My topic is curvilinear motion. What is this? It is motion where a mass is traveling in a curved path. Since I like cycling, I'm going to use this as my illustrating example to make it more interesting for myself. If you don't like cycling, here are some cats. Okay, that's all you're going to get. Back to the noble and illustrious sport which is cycling and the courageous men who make it happen. Okay, firstly, a quick discussion of coordinate systems. Here are some guys traveling in a curved path. Generally for this type of motion, we do not use standard Cartesian coordinates. If we did, we would end up with a lot of unpleasant trig functions since the direction of motion is not in line with the Cartesian coordinates. We use polar coordinates instead. A reference point and line are chosen and the distance r and angle theta are measured from them. Motion and position are measured in terms of the radial direction, er, and the direction at 90 degrees to this, e theta. Alternatively, path coordinates can be used where the motion is measured with respect to vectors tangential and normal to the direction of travel. In the case of motion around a circle, polar and path coordinates are equivalent. Motion around a circle is the simplest case of curvilinear motion and can be used to give a general or approximate idea of motion in a curved path. The polar coordinates for position, of course, can be differentiated to give the velocity and acceleration. Consider a cyclist going around a bend in the road. Even if he takes it at a constant speed is not constant velocity and the velocity is continually changing direction. Hence there is acceleration, and by Newton's second law there must be some force acting which lets the guy round the corner. This force is called the centripetal force and acts inwardly in the radial direction. For the case of the guy going at constant speed in a circle, Newton's second law comes out as shown. Since there is no change of radius or speed, many terms are dropped. Where is this force coming from? It's coming from friction between the rider's wheels and the road. Since there is no movement in the radial direction, this force can be roughly treated as static friction. Static friction is less than or equal to the coefficient of static friction times the normal reaction force between the bike and road. The frictional coefficient is a constant which depends on the road surface and the tire. In reality, it is more complicated than this depending on elastic deformations, shape, and orientation of the tires. What can go wrong? Gravel or ice on the road can reduce the friction and cause the rider to slide out. Or the rider could be traveling too fast. To travel around the same curve at a higher speed, a greater centripetal force would be required, according to the formula. This might not be possible. Again, the rider might slide out if they are leaning, or else be unable to make the turn and simply ride off the road. Indoor velodromes have banked tracks to allow for greater speed. Since the road surface is now at an angle, there is a component of the normal reaction force which is acting radially. The centripetal force is therefore increased, allowing for greater speeds. Why do riders lean in when cornering? Leaning in shifts the center of gravity so that the sideways torque on the bike and rider balances out their moment of inertia, which is acting out, keeping them stable. What about taking a good line through a corner? Cyclists favor a so-called classic racing line through the corner. They start on the outside of the road, travel to the inside at the apex of the curve, then return to the outside. Assuming a circular path, this basically maximizes the radius, allowing for a greater speed through the corner. This isn't necessarily the most favored path in motorsports, where drivers may want to take a shorter, sharper corner in order to have a longer period of time on a straight. But road cycling is an endurance sport, and maintaining speed is important. Any power required to accelerate out of a sharper corner must come from the rider. This is particularly true if the rider is descending. He simply can't get the speed back if he brakes too much. Finally, a bike is just a point mass. Some other issues arise because there are two contact points with the ground. When the bike brakes, there is a longitudinal torque about the center of mass. The normal force pushing up on the front wheel must be significantly greater than that on the back wheel to balance the torque and counter the tendency for the bike to tip over its nose or its front. However, since the frictional forces acting on the wheels are proportional to these normal forces, and so lower on the back wheel may lose grip before the front wheel and slide out. This is similar to oversteering in cars, except bikes are less stable. Severe braking could also cause the rider to fly off the bike over the handlebars, although this is unlikely unless the front wheel is stopped totally, like in a collision. In conclusion, I have discussed simple curvilinear motion as it relates to cycling. Maybe I could have spent time on the polar coordinate derivations, but this is a video and I don't want to.